All right, so velocity versus time graph on the left. I would like a reasonably drawn and accurate position versus time graph, highlighting as much reasonable information that you can get from the velocity versus time graph. But I would also like the appropriate functional relationship to go with each. You guys know what I'm saying? Something as a function of t for the velocity graph and something as a function of t for the position graph. We should know what we're doing here. The motion equations are on the board, the 5 Galilean, but only 2 of them are actual motion equations, which I talked about on Thursday. So look over there as your inspiration for what I'm looking for a functional relationship, and you have 60 seconds to do this. It had to be able to be shown that when I take the derivative of the position function, I get the velocity function. These are all based on the same math. Calculus isn't not algebra, it's just more algebra. So it has to produce the same answer. Now, I know that that's not why it works, but it's in support of that it works. Okay, so I hope so. Before we go on any further, I find it always best to make you practice this again, to make sure you got it down, and to maybe throw you a loop here or there. So we're going to practice this real quick. Let's just imagine I have this function. This is my functional position as a function of time. Can you find me the velocity function?
Yep. Is third term for 3t is the exponent of -2?
Sure is.
Thank you.
All right, bunch of you got it already. That's fantastic. Considering I have limits on time, I think it might be okay to give this a shot. I'm not going to write out all the same things I did before. The only thing that's important are the t's. Everything else is going to be treated as a constant. So I'll go to my first term, because I'm taking the derivative with respect to t of the whole thing. But I remember it can be distributed. So, but that's going to give me the velocity function. So here we go. Bring the 4 down. -2 times 4 is -8. T to the 4 minus 3, 4 minus 1 is 3. That's my first term. Move to the next term. Bring the 3 down. 3 times 6, 18. T to the 3 minus 1. 3 minus 1 is 2. Excellent. Go on to the next term. Just because the exponent is negative doesn't mean this doesn't work. I said it works for all polynomials. So it works here just fine. Bring down the -2. -2 times -3 is +6. T to the -3 power. I still subtract 1. The process doesn't change regardless of the exponent's positivity or negativity. 4 is a constant. Its derivative is 0. This is the velocity function. All good?
Yeah.
What's the acceleration function? acceleration is the slope of velocity. So you just do this again. If v equals dx dt, because velocity is the slope of position, acceleration is the slope of velocity. It's just going to be the next thing. I'm going to take the derivative again. How we doing? Not even walking around. So we want to tell me what the first term is? First term.
Negative 24t squared.
Negative 24t squared. Somebody raise your hand, give me the second term. Go ahead.
Plus 36t.
Plus 36t. Somebody else give me the last term. Go ahead.
Minus 18t to the negative 4.
Minus 18t to negative 4. Excellent. Excellent. Not a problem yet? Okay. So let me just throw a few things at you, okay? How about a question like, where is the object when the velocity is 0? Would you know what to do to get that answer? You see, I have a position function that's related to time. I have a velocity function that's related to time. And I have an acceleration function that's related to time. So when I asked, where is the object when the velocity is 0, you'd probably have to figure out when is the velocity 0 first. Get some times. And then once you had those times, use them here to figure out where the object is. Does that make reasonable sense to you guys?
Yeah.
You follow along with what I'm suggesting. Now, I'm not going to ask you to find the zeros of a function like this, but I am going to suggest that you could find the zeros of a quadratic function. I think that's not unrealistic, so I think we could probably work within that kind of area. So zeros of quadratics, zeros of linear functions are fair game. I could expect more, but it's pretty, I don't want to be spending so much time on the minutia of this mathematics. Does that make sense? So I will ask those kinds of questions. That's in your homework right now, that idea. Now, here's what I want to see if we can go a little further. You learn the polynomial process for the derivative. Do you kind of see there's a pattern to it? If I have velocity equals 6t squared plus 8t, let's say plus 2. It should not be hard to get the acceleration function, right? We just talked about that. We know that this is applying the derivative. But what if I wanted to go backwards to what was there before, the position function? Can you kind of guess at what must have been there before in order for the derivative to have given you this function? Can you try it? We almost there? Let's see. First term, 2t cubed. Second term, 4t squared. Last term, 2t. Actually not the last term. Why? Somebody explain it to us. Go ahead.
You have a constant in the position function and it gets taken out.
Right. How are we to know whether there was a constant there before? Now, something to keep in mind, we've been saying this the whole time, right? The whole time we've been saying we don't know where the object actually starts on the position graph. That information isn't contained in a velocity graph. That's true about the function as well. We don't know where the initial starting position of the function is. There might be context clues to get it, but we might not necessarily know where it is. You have about 80% of what you need to do those derivative problems. Maybe start taking a look at those, okay? So it's just running the process backwards. Bye, folks. Have a nice day. Stay dry. Maybe. Bye. Have a nice day.